Okay, so we talk about substitution method. This is the method to solve the recurrence. So, we have seen a recurrence which we are obtaining from the say merge sort. So, we have seen the time complexity of merge sort. If we want to sort n a array of size n, then the recurrence we got T n by 2 plus theta of n. So, this is the merge cost and this is the cost for recursively solving two subarrays. Okay. So, now the question is how we can sort this how we can solve this type of recurrence. So, we have seen one method which is recursive tree method. So, in that recursive tree method we have seen that. So, if you take this as C n, then we have seen T n is basically C n T n by 2 plus T n by 2. Then this is again a problem of size n by 2. We further reduce this problem into sub problems. So, okay, so this is basically C n by 2, C n by 2, and it will be T n by 4, T n by 4, T n by 4, T n by 4 like this. So, this way it will continue up to it reach to the constant T 1. So, C n by 4 all are C n by 4 in this level. So, it is ending at T 1, all the branches of this tree are ending at T 1, and T 1 is basically the problem of size 1, which is theta 1. Cost of that to solve that problem is theta 1. Okay. So, now the time complexity runtime is basically sum of these all nodes. So, to make the sum we have seen we can take C n, sum of the levels, and we know the height of this tree is log n. So, basically it is giving us a n log n algorithm. Okay. So, this is the recursive tree method which we have seen in the last lecture. This method has some drawback in the sense. So, this is not a probable method in the sense. So, we are seeing this is C n, C n, C n. So, what is the proof that in the ith level also, in the general in the ith level also it will be C n. So, that proof we are not doing here, unless we have to prove that by some way like method of induction or something, or we can just say this is giving a rough idea of the solution. Okay. So, this recursive tree method is not a foolproof method in that sense. So, today now in this lecture we will talk about a substitution method, which is basically a method by induction, mathematical induction. So, we will prove our solution by mathematical induction. So, basically it has following steps. So, this is a general method. So, it has following steps. So, we first guess the solution, So, basically we have given a recurrence, then we first guess the solution. Okay. That means, we assume this is the solution. So, then by the method of induction we verify our solution, verify the guess by the method of induction. So, mathematical induction. We know mathematical induction. So, induction means anything we want to prove in terms of n is the natural number, any property in terms of n. Actually, there are two versions of mathematical induction. First version is, suppose we want to prove some property, that property is P n in terms of n, where n is a natural number. Natural number means 1, 2 up to n up to infinity. Okay. So, we have to prove some property in terms of n. So, for that mathematical induction is telling there is a base case. So, in the base case we prove that it is true for some lower value of n, that is we can prove that the P1 is true. Then we have induction hypothesis step. So, we assume that Pk is true. There are two versions for all k up to n. So, that means Pk is true for k is equal to 1 to up to n minus 1. Okay. Then if we can prove that Pn is also true, that means if we can prove that Pk is true for k is equal to n plus 1, if we can show that, then we are done. Then we have a base case, it is true for 1. So, that means it is true for, this is one version. Another version is if you assume that Pk is true for n is equal to k is equal to n, and then if we can prove it is true for n is equal to k n plus k is equal to n plus 1, then it is true for all n. So, we will take this version of the induction method. So, we assume that our result is true for all k up to n minus 1, that means before n, and we need to prove that it is true for n. So, that means we need to show Pk is true. If we can prove that, then we are done. Then by the method of induction we can say this is true for all n. Okay. So, this is the what we know is this is the method of induction. So, we will use this to verify our proof by the help of induction. So, we first given a recurrence, we have given a recurrence, we first guess the solution, okay, and then we will try to justify our, we will try to verify our guess whether this guess is correct or not, and that we will do by the method of induction. And also we have to have the we have to solve the constant based on the base case. Okay, so now let us take an example, then it will be more clear. Okay, suppose we have a recurrence like this, Tn is equal to 4Tn by 2 plus n. Suppose this is our given recurrence, and we need to solve this recurrence by method of substitution method. Okay, so step 1, guessing step. Suppose we are guessing the solution is big O of n cube. Suppose this is our guess. Now we need to verify this guess whether this is correct or not by the method of induction. So for that, what we do? We assume, this is the assumption, we assume, this is the assumption, or this is also called induction hypothesis. We assume that Tk is basically order of k cube for all k up to n minus 1. So this is strictly less than. So we can say up to n minus 1, or if we strictly less than. So this is basically k is equal to 1 to up to n minus 1. This is our assumption. We assume that our result is true for all k up to n minus 1. So that means what? This means this is Tk is less than C k cube. This is for all k up to n minus 1. So this is our induction assumption or induction hypothesis. Now we need to show, we need to prove or show that Tn is also less than Cn cube. If we can show this, then Tn is basically big O of n cube. By assuming this, if we can prove this, then by the method of induction we can say this is true for all n, all natural number n. So, that is the way we proceed. Okay, so, let us try that. So, we need to show this, this is not yet done, we need to show this. So, we have this, so let us, so this is our, we have this induction hypothesis, induction assumption, we keep this. Now, we write this our recurrence is basically 40 n by 2 plus n. Okay. Now, we use this induction hypothesis. Now, this is n by 2, n by 2 is less than n. So, n by 2 is k, which is less than n. So, we can use this hypothesis. So, this is basically less than equal to 4 into c, n by 2 is k, k cube plus n. This is using the induction assumption or induction hypothesis. Okay. So, this is okay. So, this is basically equal to, so c n cube by 2 plus n. Now, this we want to be less than equal to c n cube. If we can show this, then we are done. Then this is the, so for that this we must able to write c n cube minus something, okay, and this quantity should be greater than 0. If it is greater than 0, then we are through, then we can say this is less than c n cube. So, let us check what is this quantity. This is basically c n cube, this is c n cube by 2 minus n. Okay. Now, c is in our hand, c is a constant which we can play with, positive constant. So, if we just choose c to be, if we choose we choose c is greater than 2, then if we choose this, then this guy is greater than 0 and then this is less than this. So, done. So, that means by taking this assumption we have shown this is less than c n cube. By taking this assumption we have shown this result is true for k is equal to n also, and we can easily check the base case. Then, so the result is true for all n. So, that means T n is basically big O of n cube. Okay. So, the solution of this recurrence is big O of n cube. So, this is the method, but basically we are using the mathematical induction. Okay. Now, we want to, because we have guessed this is order of big O of n cube. Now, we want to guess whether it is big O of n square or not, because this is our, we can have any guess. So, then we have to justify our guess by the method of induction. So, this is our recurrence. So, big O of n cube, big O of n square is also basically big O of n cube. So, we want to see whether we are getting this solution as big O of n cube or not. So, this is our new guess. Now, we want to guess whether T n will be big O of n square or not. So, this we guess. Okay. So, again we have the assumption step or the induction hypothesis step. What is that? So, we assume this is true for all k up to n. So, that means k is equal to 1 to up to n minus 1. Okay. We assume this our result is true for up to n. So, that means this means T k is, this is our induction hypothesis, this is our assumption or induction hypothesis, or this is our assumption. Okay. So, that means T k is basically less than equal to c k square for all k less than n. Okay. So, this is our assumption. Now, what we need to show? We need to show that, so we need to prove, that Tn is order of n cube, that means this result is true for k is equal to n. So, that means we need to show that T of n is less than equal to C of n square. If we can show this, then we can say Tn is order of n square. Okay. So, how to show this? So, this is our recurrence, we will use this recurrence. So, this is our k, n by 2 is less than n. So, this is our k. So, we can use this induction hypothesis. So, this will be basically, so this k is n by 2 which is less than n. So, we can use this induction hypothesis, this is 4 into C n by 2 square plus n. Okay. So, this is basically 4 cancel C n square plus n. So, now we want this to be less than equal to C n square in order to get this result. Okay. In order to get this result, we want this to be less than equal to C of n square. So, for that what we need? We need this should be written as C of n square minus of something, and that something must be greater than 0. But what is that? That is basically minus n, which cannot be greater than 0, because n is natural number, n start from 1 to 3 like this. So, the minuses cannot be natural numbers. So, this is wrong. So, this cannot be less than this. So, this is not true, wrong. So, then what will be our conclusion? So, if this is wrong, can we just say that Tn is not equal to big O of n square, or what? Because we are not achieving this. We took the assumption that this is for up to n. Now, we try to prove it, this will be true for n also, but we are not achieving this. Okay. So, can we conclude that this will be not solution of this is not big O of n square, or we have something to say over here in this bound. So, this way we cannot achieve this. Now, the question is, we can tighter this bound, we can have a tighter bound than this. See, big O of k square, big O of k square means not only this. So, this way we are not achieving that, that is clear. So, but we can tighter this bound like big O of n square. So, big O of n square. So, this is also big O of n square, say 5 n square minus 10 n. This is also big O of n square, because we ignore the lower order term, then we ignore the leading coefficient. So, that means, so this bound we want to make it tight. So, we assume this is true, big O of k square. Now, here we just take, instead of this bound, we take little tighter bound. So, we take this to be C1 k square minus C2 k, because that is also big O of k square, because this is also, this is the lower order term anyway, we are going to ignore the lower order term. So, this is also big O of k square. So, we will take this tighter bound, and then we will see whether this will help us to achieve that. Okay. So, just we assume this is a big O of k square, and big O of k square means this also. Earlier bound was, this is the more tighter than the earlier bound, and with the help of this bound, this tighter bound, we want to see whether we can justify this. This is the solution is big O of n square. Is this clear? So, this is basically we just this is our induction hypothesis step. So, this is basically true for all n less than n. So, this is basically k is equal to 1 to n minus 1. Now, we use this bound here to achieve that. So, let us try that. So, let us write our recurrence. So, this is our induction hypothesis. So, let us write our recurrence T n is equal to 4 T n by 2 plus n. Okay. So, now this is also k, which is n by 2. Now, we assume the induction hypothesis. So, this is basically less than equal to 4 C 1 k square. So, n by 2 square. So, this we can take another bracket minus C 2 n by 2 plus n. This is we are. So, this is basically we are using this. This is we are using the induction hypothesis, the assumption. This assumption we are using. Okay. So, now, so this is basically what? This is basically, so this is cancelling out. So, C 1 n square minus 2 C 2 n plus n. Just we are simplifying this. Okay. So, now, so this is the assumption we made. So, what we need to show? We need to show that this is true for k is equal to n also. That means, we need to show. So, we need to show so that T n is less than equal to C 1 n square minus C 2 n. If we can show this, then we are done. So, that is we want to achieve. So, we want to show T n is less than this. So, in order to do that, so this is basically we want to show this is less than equal to C 1 n square minus C 2 n. Okay. So, to show this, we can write this as this we must write as C 1 n square minus C 2 n minus something. So, this is the quantity we are looking for, minus something, and this if this term is greater than 0, then we are through. Then we can say this is less than this, then we are done. Okay. So, what is this term? This term is basically C 2 n minus n. Now, C 1 C 2 is the positive constant we can play with, we can choose C 1 C 2. So, if we choose just C 2 is greater than 1, then this is positive. We choose C 2 to be greater than 1, then this is positive, then this is done. Then we achieve this is true for k is equal to n also. Once we achieve this is true for k is equal to n, we assume this is true for k is equal to 1 to n minus 1. Now, we achieve that this is true for this bound, this is little tighter bound the earlier one, this is true for k is equal to n. So, the result is true for all natural number. So, that means, the solution for this is basically big O of n square. So, this we prove by the help of mathematical induction. Okay. So, this is the big O of n square. Now, we want to see whether this is big theta. So, for big theta, what we need to show? We need to show this is big omega. So, basically we want to achieve this. So, this solution we have seen this is big O of n square. Now, next we want to see whether this is big omega of n square, and if both this satisfy, if this is big omega and big theta, then it is basically big omega and big O, then it is basically big theta of n square. Okay. So, now the question is how we can show this is big omega of n square. To show this, we will follow the similar path, similar way. So, we guess, this is our guess, we guess that Tn is equal to big omega of n square. So, that means we assume that Tk is basically big omega of k square. Okay. And so, we will do the same thing, this is the mathematical induction. So, we will have this is greater than equal to some C k square, then we will try to, so this is true for all k less than n, then we will try to show that Tn is greater than equal to C n square, or else we have to try it at this bound. So, this way we will continue and we will get, we can easily prove that Tn is equal to big omega. This I am leaving you for exercise, just complete it and we can show that this is a big omega of n square. Once we achieve this is big omega of n square, big omega of n square, we have seen this is big O of n square. So, both will give the solution as big theta of n square. So, this is the substitution method. So, this is a foolproof method in the sense here we are using by taking help of mathematical induction, we are justifying, we are proving our recurrence is true for all n. So, we are, so basically it has two main steps, one is assumption, we have to guess the solution. So, where from we can guess the solution, this recursive tree can help us to guess the solution. Suppose we have a, this is our say recurrence. Now, initially we guess whether it is n cube, one can guess whether n square, n to the power 4. So, how to get a guess? So, for that guess one can take help of the recursive tree, and the recursive, once we get some solution of the recursive from the recursive tree, then we can justify the solution by using the mathematical induction. So, that is the substitution method. So, for the guessing purpose we can take help of the recurrence tree or recursive tree. Thank you.